Alright, hello, this is Mr. Hebner, and we are doing notes on galvanic cells and how to make those. So, here's an example question. It says, sketch a galvanic cell and label the electrode solutions, the flow of electrons, and the flow of ions. Alright, so first of all, what we need to do is kind of make some half reactions for this. So we got redox, or oxidation and reduction half reactions. Alright, so we got to might be helpful to write the oxidation numbers. Doing the basics, nickel solid is 0, copper 2 plus is +2, +2, and copper metal 0. Alright. So if we're going from nickel to nickel 2 plus, what's happening? Oxidation. It's losing electrons, becoming more positive. So nickel solid reacts to form nickel +2. And if it's electrons, there we go. And we're losing how many electrons? 2. Alright, so this is oxidation. So then the other one's got to be reduction. So we're going from copper 2 plus all the way to copper solid. And we're dealing with 2 electrons, and it's reduction, so it's being reduced. So it's gaining electrons, yeah, reduced. All right. So, remember the voltaic cell is kind of like this. You got your 2 chambers, your 2 half cells connected with a salt bridge and a voltmeter. And there's that acronym. Anybody remember that acronym? Yeah, we got anode, CPR, fat cat. So what does anode stand for? Anode negative oxidation. Alright. So if we got an anode negative, that means oxidation is occurring here. Alright. And then with CPR,
cathode positive.
You got it. Cathode positive reduction, CPR. So anode negative oxidation. So we got oxidation is nickel. So I got to build this little cell. There's my beaker. There's my beaker. There's my electrode. Here's my voltmeter. Oh, gotta do the salt bridge. There we go. Alright, we said that on the left side is going to be our, anode? And that's our oxidation, which is right here. So, or it doesn't have to be on the left side, you can put it on the right side. It just means the flow of electron is going at that direction. So, let's put it on this side. So we got nickel. And then the other substance is copper. Okay. And then the solution, what would be here? We got copper, or copper here, and then the other side is it doesn't give us a specific, so we're just going to put our copper 2 plus aqueous there. Then we got nickel 2 plus is the aqueous. What else do we got to do? So sketch a galvanic cell, label the electrodes. We labeled them. Oh, which one's the anode? The one that's being oxidized. Alright, so when we said oxidation was nickel, we'll call this one our anode. Oh, once we know the anode, we know the cathode. CPR, positively charged reduction. Fat cat, does that talk about the flow of electrons? Yeah, what does fat cat say? From anode to cathode. There we go. From anode to cathode. So that means our arrows are going that way. And technically it's 2 electrons. 2 electrons. So much to remember. And then when we do electrolysis, reverse a lot of it. Alright, so we got labeled electrodes, solutions, the flow of electrons, and the flow of ions. So, alright, so if the flow is going this way, is it nickel aqueous turning into nickel, or nickel turning into nickel 2+? You got it. So I'm going to draw my arrow pointing from nickel to nickel 2+. And on the reduction side, where's the ion flow? You got it. Cu2+ to Cu. So what's happening is our nickel cathode is going to get smaller and smaller. It's getting dissolved essentially. And our copper is going to get bigger and bigger. It's going to start clumping up, or covering the copper with more copper. And that is that. Oh, last thing. Does it say salt bridge? No, it doesn't say salt bridge. And it makes sense because it doesn't tell us what salt we're working with. So some sort of salt we're going to put there. Sulfates are common salts. So we'll put K2SO4. Alright, that wasn't too bad. That was taking our half reactions and putting it into an application of an actual voltaic cell. Alright. So here's another one. We got the 2 half reactions in a voltaic cell. Oh, they give us the half reactions. Well, that's convenient. So the way they drew this half reaction, zinc, is that being oxidized or reduced? Oxidized. I'm so glad they gave us that, because it would be kind of tricky. You wouldn't be able to really figure it out. I know. Unless you had the electrode potential values. And when I was doing this example, I was trying to find, they don't give me electrode potential. I think this is like an AP example. But in your data booklet on page 23, it has all of the standard electrode potentials, and I couldn't find it for ClO-. So you're not going to be asked about ClO- in IB. So next year I'm going to have to think of a different example. But it's the same concept. So we got zinc forms zinc 2+ plus 2 electrons, and that's being oxidized. So therefore, this is being reduced. And what is this? Let's see, plus. Oh, okay. Why don't we find the oxidation numbers of each of these? So oxygen is -2 always. And what can we add to -2 to get overall 3 minus? -1. So chlorine's got to be -1. So is chlorine being oxidized or reduced? No, it's just spectating. Just spectating. Oxygen goes from 2- to 2-, just spectating. But hydrogen here, +1. Oh, this is going from +1 too. All right. Let's not worry about that. So we just, according to this problem, we just need to build the unit cell. And we got an electrode. Alright. And we know, well, why don't we just put zinc on one of them? Alright, let's put zinc right there. Alright. And then zinc 2+. And if zinc's being oxidized, is it the cathode or the anode? You got it. Anybody know that acronym? Oh, anode. Anode. Negative. Oxide. You got it. Anode. Alright, so then the other one's the cathode. And we got solution. So what's that acronym for the flow of electrons? Fat cat. Alright. Cathode to anode. Are you sure?
Anode to cathode.
Okay. Anode to cathode. So the way we drew it, we're going to draw it going this way. So it's good to review those acronyms. We're going to repeat those until we know them. All right. So which way are the ions going in this case then? Because zinc is being oxidized, so the flow of ions would be, for the zinc at least, solid to aqueous solution. You got it. So which makes sense, because anode side is typically always going to go from the solid to the aqueous solution.
Will it always?
Yes. Yep. Let's see. So then on the cathode side, the flow would be doing the opposite. And let's not worry about labeling the ions. This is an AP example. You're not going to have that in IB. But you get the idea. Next year I'll switch the example. So I think I pulled it out of Zoom doll. Questions on that? All right. Cell potential. Anybody know what this is, or you just want me to write it down?
The potential.
Yep. Oh, okay, you got it?
No, I'm kidding.
Electrodes. So it's basically the difference between the two potentials of these electrodes in a voltaic cell. That's it in a nutshell. Let's get the full definition out. Electrode of a cell. It is the voltage. You got it. All right. So electrode of a cell rises due to the transfer of electrons to the external circuit of a cell that has not reached equilibrium. All right, and the units are in volts, just as Mr. Dobson was saying. There's friction through the wire, wastes some of the potential energy of the cell, but it's measured E cell is almost always less than the maximum cell potential. And the cell potential is always positive. So you're not going to have a negative E cell. It's always going to be positive. So it depends upon the reactions, like the half reactions, is it oxidation reduction of zinc and hydrogen, or copper and nickel, the concentration, so the molarity is an impact, and then the temperature. Yeah, so this would, all of the ions would just kind of pile up. Where's the flow going? It would just pile up, and then eventually not do anything, and the flow would die because there's nowhere for the charge to go.
Would it just make it slower then?
It would slow down until it stops. So, but the salt bridge allows the ions to travel back to complete the circuit so that you can actually have a charge. So. Alright, standard reduction potentials. So that's what I kind of showed you here on page 23. All those are standard electrode potentials. And let's see. You know, we got negative ones here and positive ones here, but the electrode difference, what was that we were talking about? Yeah, the difference is going to be positive. Yeah, that was the table. So the standard conditions are always 1 ATM atmospheres, 1 molar solution, and 25 degrees Celsius. If you don't have those conditions, you're not going to have a standard cell value, potential value. So we can sum them to find overall potential of a constructed cell. So your electrode potential of the cell is cathode plus anode, essentially, or the electrode potential of the reduction side plus the electrode potential of the oxidation side. That's what that's saying. So you might want to highlight or circle that. That's the main idea of those type of problems. Did I switch it? Is it table? Yes. Okay. So this is table 24, page 23 of the data booklet. Alright, so we're going back to the previous. Was that our original? I think that was our original. Zinc and, no, it was nickel and copper. Well, same idea. So, alright, half reactions are, so zinc is going from 0 to +2, that's being oxidized. So the oxidation, zinc solid to zinc 2 plus 2 electrons, and then reduction, where is it? Copper is going from +2 to 0, +2 electrons. All right. So we got the electrode potential difference. We got to do reduction, cathode minus or plus oxidation. All right, so our reduction is this one. So we got to figure, all right, copper 2 plus. Looking at our standard electrode potentials. Oh, copper 2. Oh, this is 1 electron. Oh, all right, so there are 2 different coppers, so be sure of that. This is where it's losing 2 electrons. The first one's where it's losing 1 electron. So 0.34. And we said copper was being reduced. So reduction plus oxidation plus 0.34. Alright, then we got oxidized zinc. Zinc, zinc, zinc. Here it is, negative 0.76. So what would our E cell equal? Anybody? Negative 0.42. Yeah, that's absolutely correct. So we got 0.34 was our reduction, and negative 0.76 would be the oxidation. But the way it's written, it needs to be plus 0.76, because here it's written as a reduction equation, and here it's an oxidation. So if it's written as a reduction, but we want to show it as an oxidation, we just flip the charge, 0.76. Because your E cell should always be positive, so that's positive. So that changes our value, 0.34 plus 0.76 equals 1.1. All right. So let's try this one. We got iron to iron 2 plus. So what's happening there? 3 plus to 2 plus. Is that reduction or oxidation? Reduction. All right. That's aqueous. Reacts to form, again, another aqueous, but plus 2. So if it's being reduced, we're adding 1 electron. All right, then we got oxidation is the copper, and that's going to copper 2 plus. And we're losing 2 electrons here. Okay, what's the problem here? What's different from here? You got it. So the reduction has 1 electron being transferred, and the oxidation has 2. So we got to balance it. You got it. So we're going to put 2, 2, and 2. That balances it. So what do you think that does to our electrode potential? E values are not changed when half reactions are multiplied by integer. You got it. So it doesn't change your electrode potentials. All right, so what are electrode potentials? We got to do reduction minus oxidation. So we're doing the iron, so we got to look for iron. You got it. Reduction plus oxidation. All right. Looks like there it is, plus 0.77. And then the other one is copper, and we're doing the 2 electrons being lost. That's 0.34, but let's take a look at that. Let's see. So what's, oh, you guys don't see it. All right, so we're right here. Copper 2 plus 2 electrons equal copper solid, but here where copper solid equals copper 2 plus. So what do we have to do to this? Nope, we don't double it. No. We flip the sign. You got it. Because here it's being reduced, but here it's being oxidized. So you can think of it as well, yeah, you could just think of it as reduction minus oxidation. That's how I thought of it, and sometimes, or think about it where it's got to be the oxidation version, so then you flip the sign. Kind of the same idea. All right, so that's going to be negative 0.34. Anyone have questions on that? Why it's negative instead of positive? So the overall answer should be positive always. 0.77 minus 0.34. Where are we? E cell. There we go. And when. All right, moving on. We got example. Describe the galvanic cell based on the following half reactions. Okay. So, looking at this, these are both negative values. So, well, we got negative 0.403 cadmium. So I'm looking for cadmium. Oh, it's not on there. All right. We got 10. Is there 10 on there? Okay, we got 10. So we'll go with 10. 10 is right here. We're adding 2 electrons, so this is the reduction. It's negative 0.14. The potential 0.14. So it's negative. And so this is the, what, oxidation or reduction? Reduction, you got it. So what's happening here? Reduction. They just rounded it to 0.4, 0.136. So that's our reduction. So that means they don't give us, cadmium. But I don't think that matters because they give us the electrode potential here. But we know this is oxidation because of what we do have. So to find the potential difference, what is it? Is it reduction minus oxidation or oxidation minus reduction? Reduction minus oxidation. All these things to remember. Oh my gosh. All right. So reduction minus oxidation. So this is going to be reduction plus oxidation. Reduction plus oxidation. All right. Negative 0.136 plus, but so this is reduction here. But if we're talking about the oxidation version, then we'd have to flip the sign. So these are both the reduction side of things. So oxidation version, flip the sign. Because, wait a minute, if I add 2 negatives, then I'm going to get a negative potential difference, and that can't happen. It's got to be positive. So we're flipping the sign, negative turns positive, positive 0.403. So now, okay, that looks like we're going to get an answer that fits the theory. Okay, 0.403. You can't see that. Oh, you can. Minus 0.136. All right, 0.267. Is that what you guys got? All right, so determine the reactions that occur at the anode and cathode. All right, so we know reduction and what's oxidation. So then we got to think, yeah.
When do you flip the signs?
So, good question. When do you flip the signs? So, when you come across where I'm adding 2 negatives, I'm going to get a negative answer. I know that can't be the right answer. So I'm going to flip one of the signs. And I know tin, they don't give me cadmium, unfortunately. But fortunately, they give me tin plus electrons. All right. So that's negative 0.14. So that's a match. And so that's reduction because I'm adding electron. Therefore, my cadmium probably has to be oxidation. So, if it's oxidation, like right here, you're adding electrons on the reactant side. Right here, let's see. Oh yeah, it's not on there. Oh, oxidation. So these are all reductions on here.
Yeah.
Oxidation is the opposite. So since we know that this is reduction, so if we're saying it's the oxidation version, then we got to flip the sign.
Okay, and because the other one's given,
the other one's given in the reduction form. So
on here.
On here, yeah.
So we're gonna assume the other one's the oxidation.
Exactly.
Okay.
All right. Let's see. Determine reaction that occur in. Okay, which one would occur in the anode? So we're going anode, negative, oxidation. Okay, so then this would be the anode. And then CPR, cathode, positive reduction. That would be cathode. Alright, calculate the overall cell potential. We did that, E cell. Draw a diagram of a voltaic cell including solutions. Alright, we'll just draw a little mini version of this. Alright, I'm just going to pick one side. Let's do cadmium. And then we got cadmium 2+. And the cadmium side was oxidation, the anode. And then the other side is the cathode, which is tin, and then tin 2+. And we got to do fat cat. What's fat cat say? Anode to cathode. You got it. So the electrons are going anode to cathode, which means cadmium to cadmium 2+ or cadmium 2+ to cadmium. Cadmium to cadmium 2+, right? Okay. Alright, and that would mean that tin is precipitating out into the solid. And then there's write the line notation of the cell. So the line notation coding it, yeah. So, yep. But it would be coating tin with tin, so you wouldn't really notice a whole lot. It's just be getting a little bit bigger.